In this section, we're going to look at multiplying radical expressions. Let's look at the product rule for radicals. For any real numbers with an nth root of a number a and an nth root of a number b, the nth root of a times the nth root of b is equal to the nth root of a times b. The product of two nth roots is the nth root of the product of the two radicands. Now, why is this the case? Let's just take two numbers and look at why this works. Let's say we have the square root of 5 times the square root of 7. These numbers don't simplify outside of the radical, but their indexes match. So we could rewrite this as 5 to the 1/2 times 7 to the 1/2. Now notice their bases don't match. This is fine because what we're saying is that the bases are different factors. 5 times 7 raised to the 1/2 is a power rule, and you can distribute back to 5 and to 7. So this rule works for the radicals as well. So we could say that 35 raised to the 1/2 is equivalent, or just the square root of 35. So let's work on some additional practice sets to see if you kind of get the idea. For practice set 1a, we have root 2 times root 5. We assume they're square roots since there's no index given, and so we can rewrite this as the square root of 2 times 5, which is the square root of 10. Now let's look at b. We have the cube root of 3 times the cube root of 9. This is equivalent to the cube root of 3 times 9, which is 27. We can simplify this one because we know that the number 27 is a perfect cube. So 3 times 3 times 3 would give us 27. And so the cube root of 27 is just 3. Let's look at part C. We have the fifth root of 8y to the third times the fifth root of 10y. We can rewrite this as one radical, the fifth root. 8 times 10 is 80. Y to the third times y to the first is y to the fourth. We can double check that 80 isn't a perfect, power to the power of 5. We have to see if there's any factors to the power of 5 in there. So we'll take 80, we'll just re-break it down. So 8 and 10. And we know that 10 is 2 and 5. So the highest power we would have would be 2 to the 4th times 5. So we can't simplify that any further. It's in its simplest form. Now let's go back up and look at part D. We have the square root of y minus b times the square root of y plus b. We can rewrite this as the square root of y minus b times y plus b. Notice I put both binomial factors inside the radical. I'm now going to multiply these two binomials together. This will give me y squared minus b squared. Now you might be thinking this can come out of the radical as y minus b, but unfortunately that is not the case. The only way you can take something out of the radical is by finding a common factor. This last example is the 7th root of x minus 3 divided by 4 times the 7th root of 5 over x plus 2. We can rewrite this as the 7th root of 5 times x minus 3, and I just put the 5 first because that's kind of common notation, and then in the denominator 4 times x plus 2. We can't really simplify this any further, but we might need to rationalize denominators. We'll talk about that later. And this challenge question, I'm going to ask you to pause the video and see if you can figure this one out on your own. The indexes don't match, but there is a way to make it a lot easier to do. So the first thing I did was find a common denominator for my fractional exponent. From there, I'm trying to figure out how I could rewrite this so that my indexes match. And now they actually do match, but I don't have matching numerators. So I'm going to rewrite this as x plus 2 over 4 to the power of 10 times 5 over x plus 2 to the power of 3, all raised to the 1 over 30. I can then write this as the 30th root of x plus 2 to the 10th over 4 to the 10th times 5 to the 3rd over x plus 2 to the 3rd. And notice that the x plus 2's can divide out in 3 sets, and you'll be left with x plus 2 to the 7th in the numerator, and the denominator will divide out